So our last presenter for part one of the session is the Associate Professor of Data Assimilation and Atmospheric Chemistry of the Department of Hydrology and Atmospheric Sciences of the University of Arizona in USA. He is a faculty member of the UA Graduate Interdisciplinary Programs on Remote Sensing and Spatial Analysis and Applied Mathematics. His research focus on investigating human fingerprints and atmosphere, and he is a recipient of several NASA Group Achievement Awards. Our speaker is also a co-chair of the Analysis of Emissions Using Observations, acronym AMIGO, activity of the International Global Atmospheric Chemistry. Ladies and gentlemen, it is my pleasure to call on our next speaker to discuss his topic entitled Towards the Identification of Emergent Properties in Atmospheric Composition Using Satellite Data, a case of megacity emissions monitoring from space. Let me call on Dr. Avelino F. Arellano Jr. Abe, the floor is yours.
Thank you, John. Let's wait for my screen to share. Can you see my screen?
Yes, Abe, thank you.
Okay. Well, thank you, John, for having me in this session. And thank you for Dr. Comiso and Dr. Talib for a nice introduction on CO2 problem, at the same time for air quality problem against the backdrop of anthropogenic activity. What I'm going to share with you today is some of my research on the fundamental direction that our research group is pursuing, and that is how do we utilize satellite remote sensing instruments and products to better understand emissions and the spatial and temporal variability of those emissions in a way that we could improve our capability to assess, monitor, report, and in fact predict the changes in this our atmosphere due to this emissions. What you're seeing there is just all of the birds are flying out there for NASA, but these are all polar orbiting satellites, and they sample the globe once or twice a day. But we'll have a revisit time for about 10 days or so. So we don't really see a lot of we don't see a lot of this. We don't observe this in terms of very high resolution in terms of temporal aspect. In 2016, the National Academy of Science, Engineering, and Medicine published a consensus science report and is identifying one of the science priority research area is to better understand emissions and its spatial and temporal variability, as well as its sources and sinks. This is just part of the report, where you see the sources on the other side, and then the societal impacts on the other side. And we really need to understand both of these processes, both the predictive capability and the feedback of these emissions to the causes. The idea is we want to attribute this cause or the impacts to causes of, especially for anthropogenic activity. This is really exemplified by the CO2 problem, and Dr. Comiso already showed you this similar graph of CO2, but this is a simulation from NASA gathered with regards to the abundance of carbon dioxide produced from fossil fuel combustion, as well as fires from biomass burning. And as you can see, you see a weather-like carbon weather pattern here. But against that backdrop, you'll see that it is only about a couple of ppm. And that is way lower compared to the background 415 ppm nowadays. So it's about a quarter to a 0.5% of CO2. And so it's akin to finding the needle in a haystack and finding really quantifying well what is the contribution of anthropogenic activity has fossil fuel CO2 in this 415 ppm of concentration. So that's a very daunting task. The way to do it, and there's two approaches for this, is the bottom-up approach and the top-down approach. The bottom-up starts with an activity, information of the activity, road transportation, power plants, and an efficiency, as well as its emission factors. And from that, you build up an emission inventory, and we use a model to input those emission inventory and calculate abundance. The top-down estimate starts with what we observe in the ambient surroundings, what we observe CO2 concentrations, air pollutant concentrations, and from that infer emissions out using the model as well. And so as you can see, there are disadvantages to this. One is it's hard to verify. The other one is that it's incomplete. We don't really have a lot of observations, although we have satellite data, but it's very hard to attribute because there's transformation that goes on and there's weather phenomenon that actually impacts that as well. It's a very strongly coupled system. What we can do is actually think about it as a systems approach, wherein we think about it as this one part, the air, as one part of the system, the Earth system, as interconnected with the other parts of the system. And we want to look at it from a bigger perspective, a larger perspective, from a bird's eye view perspective. And it's similar to an environmental Kuznets curve, wherein you see, for example, as a city evolves and develops, it requires more energy demand and material supplies and so on, and that pollution actually increases at that time. But there's a point in which there's a turning point whereas the city develops more, then you have finances, you have capability, technology capabilities to improve or control, regulate emissions. And so there are many satellites out there. This is just one of the papers showing several of these satellites. This is for air quality, OCO2, which Dr. Camisa showed. It's not here, but this is for air quality. So there's TROP-OMI, there's OMI that Dr. Talib showed. There's MOPET for CO and so on. But they have different sampling characteristics in space and time. We think about this as the five blind man. We want to really look at it from not just one part of the elephant, but in the entire thing, the entire elephant, so we can infer rigorously what's the anthropogenic impact. And so the question that I really want to ask is what can satellite data tell us about emergent properties of atmospheric composition? This is motivated by the fact that even US EPA inventory emissions are still out of sync. When I say out of sync, there's a discrepancy between what you see in the from space and what you actually report as a bottom-up estimate. And this is just one paper that we published several years ago when we look at there's actually a slowdown in terms of NOx, nitrogen dioxide emissions in the recent decade because of changes in our activity, essentially. So the idea is to look at different constituents, and the idea is to look at different parts of the system. And what if you look at the emissions and look at the abundance, and they are coupled in one specific equation. It's combustion. Combust the fossil fuel, you use oxygen and nitrogen, and you produce pollutants. Carbon dioxide is not pollutants per se, but CO, NOx, SO2, black carbon, these are all monitored as a criteria pollutant. So what if we actually look at the difference between this abundance to tell us about the efficiency of a certain city, to tell us about how it evolves across time? And so this is just an example of what we did in the past. And in the x-axis, you see the standard deviation of nitrogen dioxide columns, or XNO2. And the circles corresponds to GOSAT, this is the Japanese Space Agency's CO2 retrieval that is with the CO2 retrieval algorithm implied to this. And you can see that even when we look at the NO2, and as Dr. Talib showed, this is a very indicative of activity. And also it is indicative of efficiency. It's very correlated with CO2. And you see that China is in this realm, and then the other one, the developing countries, is in the other side. But what if we actually use CO as well? This is from Muppet CO, and the other one is from OMI and O2. You'll see actually you can differentiate, you can disentangle. The hope is that we can disentangle natural versus anthropogenic emissions. In this case, we're just looking at the sectoral contribution. Let's say Amazon is more on the fire emissions. China is in both producing high CO and producing high NOx. And so we can also look at it from a decadal point of view, and the changes that these regions can actually evolve. So you see that you have Los Angeles, Beijing, Tehran, and Dhaka, and we don't really have a lot of CO2 data, so we use GDP as a proxy. And again, you'll see that each of these regions, each of these cities have a different trajectory depending on practices, depending on technology, and of course, GDP. And so question is, can we look at this same graph with Metro Manila and other urban agglomerations in the country? We've started also looking at it from a CO2 point of view over megacities, and we've ranked, in fact, several of these megacities from the top to the bottom, and CO2 here corresponds to a measure of efficiency of combustion. You see Beijing is in the lower end, while Germany, London is in the higher end. It was very surprising to us, that was in 2013, it was very surprising to us when we look at the data, ground-based measurements and field experiments, that our values or the ratios actually correspond very well with ground-based and field campaign measurements. So it was very promising to see. We've looked at also several of these in terms of the plot that I showed you before. Manila is over here in a lower quadrant, but Beijing and Tianjin is in the higher quadrant. And you see there's a complement between the fossil fuel energy proportion with regards to renewable energy that's been used. Very interesting features that you can actually disentangle combustion efficiency between different cities. We've looked at it for China, for different pollutants. And what we found is that there is actually an evolution of the cities from a low developed city like Shenyang to a higher well-developed city like Shenzhen. And there's in fact a change in the sectors, and the sectors that really was driving this change is the industry and residential sectors for Shenzhen, which is actually more efficient relative to Shenyang. We've also looked at it from the point of view of Africa. Africa is a very interesting contrast with China. China has a very high polluted condition environment. Then Africa is, as you can see in the night lights, it's all dark. Human Development Index of Africa is very low, lots of war, but there's actually an emerging rise of anthropogenic activity in these parts of the world that cannot be seen, at least from now, from space. What we can show here, for example, is the sector, our contributions of different sectors, power plants, industry, and residential and roads, and most of it are in the road and transportation sector. But there's an increasing trend in the CO and NOx in terms of the change in the decade, across the decade, except the South Africa, which you can actually see in the night light as a big power plant emitter, big NOx emitter. We've tried to look at it from a change in decadal change in these emissions, or also in terms of abundance. The red corresponds to abundance based from satellite space-based analysis. The gray is corresponding to emissions. And you can see that the change in the present change relative to 2005 is different between what we see from space and what we see from the bottom up. And the bottom up approach is actually very correlated with socioeconomic factors, GDP, fossil fuel use, population, electrical consumption. Well, the abundance-based estimates were much confounded by natural events, natural processes, fire, lightning, and clouds. So the question really was, can we really see it from space? Yes, maybe for China, but at least from Africa, we don't really see that yet. We don't know if it's a retrieval issue, or we don't know if it's an information issue with regards to bottom-up. We can look at it from the perspective of drop, or the rate at which efficiency improves, and this is based on the power law. So if you look at the exponent here, that corresponds to the rate at which it's dropping. Sub-Saharan Africa is dropping less compared to China in terms of, again, efficiency-wise, improving efficiency. But it's still way far from China. And the emission-based and the abundance-based approach are still very different. And so the question that I want to pose is, again, for Metro Manila, but also for this. This is a new paper by the Global Carbon Project, and showing, again, the effect of COVID-19 and very detailed analysis of global daily changes due to COVID in different sectors, power plant, and residential, and industry, and of course, surface transport or surface transportation. So you can see that there's actually a nice decrease. Our question is, can we actually verify this at this scale, at this daily scales? This is from a bottom-up approach. We don't have that capability yet for the top-down approach at this scale. And so I would like to end by saying that, yes, this is a very interesting opportunity. We would very much interested to look at it for Metro Manila. And I would like to shout out the local experts in the Philippines, University of the Philippines, LaSalle, Ateneo, Manila Observatory. There's TCON site, there's Aeronet sites that's already available for us to look at, and international community is actually looking at. There's also collaborative research of these universities with international agencies like the Germans and the Americans and the Catholics and MAIS 2005. I'd like to look at this from an international activity that I'm co-chairing, which is looking at essentially these emissions and abundance, and can we actually provide a robust way to understand this in terms of predictability. And so I thank you all, and maraming salamat, and back to you, John.
Thank you very much indeed, Abe, for that very interesting and comprehensive discussion on the value of satellite data, as well as the challenges associated with it in understanding megacity emissions and monitoring from space, but at the same time, in terms of calling on for potential collaboration in the Philippines and in different parts of the world to really address this particular scientific challenge.